Hello everyone, I'm Tinghui Ouyang, a researcher from AI Research Center of the AIST, Japan. I'm very happy today to share you our study about AI quality assurance. Our presentation title is Corner Case Data Description and Detection. Contents of this presentation are organized the same as our paper, containing four major parts, such as background introduction, problem description, methodology, and the experiment analyzed. As we know, AI has been developed in many areas, including both the industries and our daily life. In this case, the safety of the deep learning-based AI models is directly related to the safety of our life and property. Well, like bugs in the traditional software, incorrect or unexpected corner case behaviors always played the important role affecting DL systems safety. For example, as the picture shows, here picture 1 shows Tesla's DL system failed to deal with the corner case. For example, dealing with a condition of white color against a bright sky. Picture 2 shows Google's self-driving car crashed to a bus since its DL system make wrong decisions on real conditions. Similar situations can be found for other companies' self-driving car, like Uber, Waymo. Bugs in traditional software and DL systems are different. In software, bugs are related to the programming code, but DL systems are trained based on data. So there are erroneous behaviors related to data itself. We can call this data as corner case data. There are many research related to corner case study, major involving two aspects. One is to study the robustness and the stability when facing with corner case data. The other one is to generate as many as possible corner case data for retraining and improving DL systems performance. As we know, it's hardly possible to generate and consider all kinds of the corner cases in the training process, even though big companies like Tesla and Google, even though they have developed many effective techniques in corner case study. However, studying a way for detecting corner case seems more feasible in AI testing. Therefore, our objective of this research is to study the corner case data description and the detection. Before this study, we need to define corner case data firstly. According to the introduction just now, we know corner case data is sensitive to perturbations, and they are easily caused incorrect and unexpected behaviors. So we can give out corner case definitions as the given formula here. It's easy to know data of the corner case includes incorrect classified data as well as the data close to classification boundary. As I just mentioned, corner case data for DL systems are related to data, so its description should be rely on data. In ICSE 2019, a paper introduced to use surprise quiz to describe the similarity of the tested data. In the paper, deep features of the DL models are taken to study data's behavior. Since DL systems can transfer both the Euclidean and the non-Euclidean data into linear separable space. This is better for data analysis. Then, the behaviors of the data in deep feature space is defined as activation trace, and the distance-based surprise quiz, namely DSA, are defined for data quality analysis. Well, it seems that data similarity with training data is an important data quality. We may make use of it for corner case description. Moreover, for evaluating corner case data detection performance, we can define a quantitative metric as corner case data coverage as defined in the given formula. In the original DSA definition, we see that DSA can be regarded as the comparison between a testing point's novelty in its belonging class and its novelty to other classes. This definition may be useful to describe the surprise of a testing data to the whole training data. However, to evaluate if a data sample belongs to corner case, its own novelty respect to all classes seems more important. Therefore, we has the first modification, which considers surprise of the testing data to whole classes independently. This is the definition of the DSA1. However, for DSA1, if the testing data X itself is corner case data, there happens to exist a neighbor XA very close to X. This may lead DSA to be a low value due to distance A equals to 0. This case is unhelpful for corner case detection. A more general descriptor should be selected, not individual point. So we propose to use the class center for DSA calculation in DSA2. This is the definition of the DSA2. Moreover, the definition of the DSA2 still has drawback. For example, facing with the unbalanced classes, the global descriptor in this DSA2 definition may also lead to mistakes for corner case discrimination. Therefore, we further propose to use the local descriptor replace the global descriptor. The local descriptor can be defined as the center of the nearest neighborhood. This is the definition of the DSA3 as shown in the slide. Then, based on 4 canons of the DSA definitions, we can implement experiment on a benchmark dataset, such as the MNIST data for digital number recognition. By calculating 4 canons of the DSA values on the last layer of the DL model, we can draw out images with high DSA values. Like the picture shows, it's seen that all these 4 DSAs has the ability of describing corner case data, since they indeed capture unrecognizable data. Moreover, using the defined corner case data coverage as the evaluation metric, coverage variance is also plotted in the figure. Moreover, calculating 4 canons of DSA values on 3 specific layers and using them for corner case detection, the AUC and OC values are calculated for corner case detection. Results shows DSA3 performs better than the others. Moreover, we can implement some study on real industry application. For example, the casting defect data. Casting defect is an undesirable result in a mental casting process. Its data is available in Kaggle. It mainly contains free images and defect images, so it's standardly used for binary classification. As the similar process, we can construct a CNN model for this problem and calculate DSA values of the specific layers of the DL model. Then, calculating the corner case data coverage and AUC-ROC values on corner case data detection. As shown in the figures, 3 layers are selected and 4 DSA are calculated. Results show that DSA indeed have good capability of corner case data description and detection, and relatively DSA3 has a better performance. That's all of my presentation, and thank you for your attention.
Hi, a very good day to everyone. Welcome to session 4, Applying ML Technologies. So we have 4 exciting talks for this session. You have just watched the video of the first one just now. So we have with us today in this first discussion session, Tinghui. So Tinghui is from the Artificial Intelligence Research Center in Tokyo, Japan. So if you have questions for the authors for this paper on corner case data description and detection, please enter your questions in the chat, and then I'll be able to ask those questions to Tinghui. So let me start the first one while we are waiting for your questions. So the first question that I have is that in the solutions that you have proposed, Tinghui, you have detected corner cases. How could these corner cases be used to improve the accuracy of the deep learning solution? For example, in handwriting recognition in the MNIST dataset.
Okay, because corner cases are defined as the high risk to make the wrong decisions in the DL models, no matter machine learning models or DL models. So they will make the wrong decision. So there are 2 ways to improve the accuracy. One is in the training process, we can maybe delete or remove the corner cases and then to retrain the DL models. And I think this is the one way to improve the accuracy. And the other way is in the testing process, because the corner cases make the wrong decisions. If we remove the corner cases, maybe we will reduce the amount of the false positive events. So I think the accuracy will be improved.
Yes, thank you, Tinghui.
Yeah.
Yes, thank you for the answer. And there is 2 questions. So the question by Luis. So following up on the question that is posted on the chat, why is it important to assess the difference between DSA1, DSA2, and DSA3? I think you have many different variations of the DSA. So what do you think to assess the difference?
I think because the way first to do this research is we based on the original DSA. That means the distance-based supervised quiz, and the authors think that in the ICSE of the 2019. So they also think that DSA is a good tool for corner case detection, but we don't think it's good enough. So we do some modification to improve its performance on corner case detection. That's why we propose the DSA1, DSA2, and the DSA3. Why it's important? Because we think that from DSA0 to DSA3, it's a progress step to improve the make a progress to improve the performance. Maybe in the future work we will develop or to find some DSA3 or to others. That's the purpose of why we doing this research. Yeah.
Okay, thank you for the answer, Tinghui. And there is another question by Per Runeson. Have you any experience from traditional system performance testing? If so, can you see any similar challenges with respect to corner cases compared to high load or special condition cases in performance testing? So There are corner case testing also in other areas in the traditional system performance testing. How different is it with deep learning? If I
Actually, we don't do much comparison right now because in traditional systems, maybe for software engineers, they have to do a lot of the research on the back. Because in the presentation, I have mentioned that in the traditional systems, maybe the bugs we can solve from the logic programming. But for DL-based systems, maybe it's different. So why we